All right, let's talk about a huge, massive challenge that's hiding right under the surface of the IoT world. It's all about data quality. And honestly, it's something that could either make or completely break the promise of our connected future.
I mean, we've all seen the vision, right? This amazing world powered by the Internet of Things, giving us smart factories, super efficient cities. A world driven by data pouring in every single second from billions of sensors. But what happens if that data is just plain wrong?
Well, this happens. $600 billion. That's how much bad data costs U.S. companies every single year. It is a mind-blowing number, and it shows you that this isn't just some small technical glitch we're talking about. It's a colossal business problem.
Okay, so here's how we're going to tackle this. First, we'll get into the IoT's dirty little secret. Then we need to figure out what good data even means. From there, we'll look at the usual suspects, all the common errors. Then we'll get into how to actually find and fix those problems. And finally, we'll talk about what it all means for unlocking the true power of IoT.
So let's start right there with that dirty secret. Because behind all the hype and the futuristic promises, there's a fundamental issue that's quietly killing countless IoT projects before they even have a chance to succeed.
Now check this out, because this is where it gets really interesting. A survey found that while 35% of the IT execs thought their IoT project was a success, only 15% of the business execs, the people who actually need the results, agreed. So why the huge gap? Well, the number one reason was that the project failed to produce valuable, trustworthy data. The tech worked, but the data was useless.
And the whole data journey, it all starts right here, with the sensors. You can think of them as the digital nerve endings of the IoT world. They're out there constantly collecting raw data on, well, everything. Temperature, vibration, location, you name it.
But from that sensor, the data has to travel. It gets beamed through all these complex wireless networks, 5G, Wi-Fi, whatever, on its way to get processed and, hopefully, turned into something that's actually useful. The key word there is hopefully, because that journey is full of danger for the data.
And here's why. Just think about where these sensors live. They're often in these incredibly tough environments. We're talking intense heat, dust, non-stop vibrations on a factory floor. The sensors themselves can fail, their wireless signal can drop, they just get old and wear out, and they can even get hacked. Every single one of these things can corrupt data right at the source.
So if data can go wrong in so many ways, what does good even look like? Before you can fix a problem, you have to know what you're aiming for, right? So what's our target when we talk about high-quality data?
First up, and this is the big one, is accuracy. It's the most fundamental question there is. Is the data telling the truth? Is the temperature that sensor is reporting actually the temperature in the room? If it's not, then everything you build on top of that data is built on a lie.
Next, you've got consistency. This is all about context. In other words, does the data make sense for where it came from? If a sensor in Alaska is reporting that it's 100 degrees Fahrenheit in the middle of January, well, that data might be technically accurate from the sensor's point of view, but it's not consistent with reality. Something's obviously wrong.
And finally, there's completeness. Did we actually get all the data we were supposed to? With sensor data, which comes in over time, even tiny little gaps can be a total disaster. If you miss just a few seconds of data from a critical machine, you could miss the one clue that would have predicted a massive failure.
Okay, so now we know what good looks like. Let's meet the villains of the story. These are the usual suspects, the common types of errors that data scientists are always battling to keep out of our systems.
Here's a quick rogues gallery for you. You've got outliers, which are like sudden spikes. Missing values, where the data just goes poof. Bias and drift, which are these sneakier, slow burn kind of errors. And then there's just noise, a bunch of random static getting in the way. We're going to zoom in on a few of the most important ones.
So first up are outliers. You can think of these as those sudden weird readings that just make you go, wait, what? They're values that are way, way outside the normal range, like a machine's temperature suddenly spiking to an impossible number for just a fraction of a second. It could be a real event, sure, but it could also just be an error.
Then we have missing values. This is when the data just vanishes, gone. Maybe the network connection dropped, maybe a sensor's battery died. For any number of reasons, you're just left with a blank space right where a critical piece of information is supposed to be. Now, drift is a much sneakier kind of error. This is when a sensor slowly, almost invisibly, gets less and less accurate over time. Its parts get old and its readings start to drift away from the real value. This one is really dangerous because it's not an obvious spike. It just gradually poisons your entire dataset without you even noticing.
So we've got our whole gallery of errors. But here's the good news. We also have a really powerful toolkit to fight back. Data science gives us some amazing techniques to automatically find these flaws and, a lot of the time, even fix them.
When you're hunting for those outliers, there are really two main ways to go about it. The first is unsupervised, which is kind of like a detective showing up to a crime scene with zero prior information. It just looks for the data points that don't fit in with the crowd. The other way is supervised. For that to work, you have to train a model first with data you've already labeled as normal or weird, so it knows exactly what to look for.
And what about filling in the gaps from that missing data? Well, again, different strategies. Intransitive methods just look at the variable that has the gap. They basically try to draw a line between the point before and the point after to fill it in. Transitive methods are a little smarter. They look at other related data to make a much more educated guess about what that missing value should be.
So all of this brings us to the final, and I think the most critical point: getting a handle on data quality. It isn't just a technical cleanup job. It is the key to unlocking the future that the Internet of Things has promised us all along.
When you boil it all down, it comes to this. All the incredible potential of IoT, the predictive analytics, the AI, the machine learning, it all hinges on the quality of the data you feed it. If you train a brilliant AI model on bad data, you're going to get bad results. It's the classic garbage in, garbage out problem, just on an absolutely massive scale.
And the stakes in the real world could not be higher. Think about a giant mining excavator like this one. If that thing unexpectedly fails, it can cost a company millions of dollars in downtime. But a predictive model that was trained on high-quality, reliable sensor data, it can spot the warning signs and flag a potential failure before it happens. That's the power of good data. It's not about charts and graphs. It's about preventing real-world disasters and creating real-world value.
So we'll end on this thought. This connected world is already here. It's generating an almost unbelievable tidal wave of data every single second. The real question we all have to ask ourselves isn't, can we collect the data? It's, is the data we're collecting good enough to build the future on? And from what we've seen, the answer to that really depends on how seriously we're willing to take this challenge of data quality.